We're going to be covering chapter 4.4 in this lecture, and that's on oxidation and reduction. And so we'll find out what oxidation and reduction is. Essentially, it's a matter of exchanging electrons. We'll learn about oxidation reduction reactions, and we're going to spend most of our time learning how to balance these redox reactions. Okay, let's get warmed up with a little bit of review. And we're asked what volume of a 1.5 molar hydrochloric acid solution is needed to provide 6 moles of the hydrochloric acid. Okay, we're using our units for this. I hope we can see that. And we would ask, are there any preliminary steps? Let's pull out that conversion factor. Remember that big M bar really means moles per liter. Then on to step 1. We're after the volume, so liters of solution. That tells us for step 2, we're looking for a number with the single unit to start the calculation with, and that would be the 6 moles of the hydrochloric acid. And now on to step 3, let's get out of that initial unit. And now comes the big question, can we go straight from moles of hydrochloric acid to liters of solution? And that conversion factor sitting right there tells us yes, we can. And for step 4, it tells us the 1.5 goes with the moles, 1 with the liters, and that would be 4 liters of solution. Next, how many grams of potassium chloride would you need to prepare 0.25 liters of a 2 molar potassium chloride solution? Again, we're using our units, and are there any preliminary steps? Yes, let's pull out that conversion factor and turn that big M bar into moles per liter. Then step 1, we're after grams of potassium chloride. And only that liters of solution is a single unit, so we're starting with that 0.250 liters of solution. And now step 3, let's get out of liters of solution. Getting this far, I hope you find is very easy. Step 1, what are you after? If you're after a single unit, then you're starting with a single unit. Then step 3, let's get out of that unit. Now, can we go straight from liters of solution to grams of potassium chloride? No, we're going to go to moles of potassium chloride using the concentration term. And then from moles, we can always go to grams. That's 2.00 moles per liter of potassium chloride solution. And the sum of the potassium's molar mass and chlorine's molar mass gives us 74.55 grams per each mole. Potassium is 39.1 grams per mole. Chlorine 35.45, so that's where we get the 74.55. For 37.3 grams. Our answer should have 3 significant figures. Don't forget significant figures. And now let's write a net ionic equation when solutions of iron 3 nitrate and potassium hydroxide are mixed. Okay, well, step 1, we identify the species present in the solution, and so from a solution of iron 3 nitrate, we have the iron 3 ions and the nitrate ions. We're then mixing it with a solution of potassium hydroxide, which consists of separate potassium ions and hydroxide ions. Again, step 1, identify the participants, meaning the reactants in the reaction. Then, let's identify if there's any insoluble precipitates that are formed, because we're only going to show those species that are changed. Well, the iron is soluble with nitrate. Is it soluble with the hydroxide? And no, it is not. So we're going to form the insoluble precipitate iron 3 hydroxide. Potassium is soluble with hydroxide. How about with nitrate? And I hope by now we know that those 2 ions are soluble with everybody. And hence the nitrate and the potassium ions remain unchanged, and hence they are spectator ions, which means that they are eliminated. Now that we've eliminated the spectator ions, we're going to rewrite the equation, and now we'll give a final balance. I see 1 iron on the left, 1 on the right. The least common multiple of 1 calls for 1 iron on both sides. Then 1 hydroxide on the left, 3 on the right. Least common multiple is 3. There's 3 hydroxides on both sides. And let's double check that a charge balance as well. 0 charge on the left, 0 on the right. That plus 3 and negative 3 give us 0 charge. Now to remind you, you might want to stop and do these questions on your own, and then we can do them together. Okay, we have sulfuric acid reacting with sodium hydroxide. It'll form sodium sulfate and water. We balance an acid-base reaction by recognizing that the hydrogen ions needs to be equal to the hydroxide ions. And so I see a source of 2 hydrogen ions in sulfuric acid, a source of a single hydroxide in sodium hydroxide. So the least common multiple of 2 and 1 is 2, so that means I'm going to have 2 hydrogen ions, so 1 sulfuric acid, 2 hydroxide ions, so 2 sodium hydroxides. We always form just 1 salt, and I can see from the 2 sodiums on the left it has 2 sodiums in it, and the 1 sulfate on the left I have 1 sulfate in it. And 2 hydrogens got together with 2 hydroxides to form 2 waters. Next we have phosphorus acid reacting with calcium hydroxide. The acid is a source of 3 hydrogen ions, the base is a source of 2 hydroxide ions, and now the least common multiple of 3 and 2 is 6. So 6 hydrogen ions requires 2 phosphorus acids. 6 hydroxide ions requires 3 calcium hydroxides. There's always 1 salt, and how many calciums are in a salt? Well, the 3 on the left says there's 3. And how many phosphites? The 2 on the left says that there are 2. And 6 hydrogen ions got together with 6 hydroxide ions to form 6 waters. And again, feel free to pause this presentation at any time so that you can do these on your own before we do them together. Okay, we have arsenic acid, which is a source of 3 hydrogen ions, reacting with lead-4 hydroxide, which is a source of 4 hydroxide ions. Okay, 3 and 4 give a least common multiple of 12, so for 12 hydrogen ions we need 4 arsenic acids. For 12 hydroxide ions we need 3 lead-4 hydroxides. There's always just 1 salt, and it has 3 leads in it. And 4 arsenates, again I get this from the left side of the equation. And 12 hydrogen ions and 12 hydroxide ions form 12 waters. Okay, using the following net ionic equation, we're asked what volume of a solution of 0.110 molar cobalt-3 nitrate is required to form 1 gram of solid cobalt-3 hydroxide. Okay, well, we have a stoichiometric problem here, and I do have a preliminary step in pulling out that concentration term. But we're going to be using our units, and that begins with step 1. We're after the volume, so milliliters. Step 2, only the 1 gram of the cobalt-3 hydroxide has a single unit. So step 1, step 2, I hope you found that easy, as I hope you find the beginning of step 3. And now comes the big question. Can we go straight from grams of cobalt-3 hydroxide to milliliters of cobalt-3 nitrate solution? No, we're relating one chemical to another, and we know we can only do this through moles. So first from grams of cobalt-3 hydroxide to moles of cobalt-3 hydroxide. And then using the balanced equation, we're going to go from moles of cobalt-3 hydroxide to moles of the cobalt-3 nitrate. And then that concentration term is going to allow us to go from moles of cobalt-3 nitrate to liters of cobalt-3 nitrate solution. And then a simple metric conversion takes us from liters to milliliters. Molar mass of the cobalt-3 hydroxide is 109.9 grams per mole, and that would be the sum of 58.9 grams per mole for the 1 cobalt, and 3 times 16.0 for the 3 oxygens, and 3 times 1.0 for the 3 hydrogens. And then it's a 1-to-1 reaction. Just because it's 1-to-1, don't let yourself think that you don't need to do that step. And then that's 0.110 moles per liter of the cobalt-3 nitrate solution, and 1 milliliter 10 to the negative third liters, base 10 number still going with the base unit. And when I put this all on my calculator, I come up with 82.7 milliliters. We should be asking, does our answer make sense? And that seems reasonable. What wouldn't be reasonable? How about 0.827 milliliters? Or 8,270 milliliters? Okay, calculate the mass of the precipitate formed when 125 milliliters of 0.150 molar sodium chloride and 150 milliliters of 0.100 molar silver nitrate are mixed. Okay, the mass of the precipitate formed, so we're looking at a net ionic equation, and we know sodium is going to be soluble with everybody, and so is nitrate, so we're looking at silver and chloride, and so sure enough, silver and chloride combine to form the insoluble precipitate silver chloride. So there's our net ionic equation. Then, as preliminary steps, we should also pull out those conversion factors, or simply extend the bar and put it over liters. Again, extend that big M bar and put it over liters. And now I think we're ready for the calculation, and we're given the information on both reactants. So this is a limiting reactant problem. So we're going to have to come up with the potential amount of both that can be formed, and the smallest amount is the maximum amount. We're using our units, and that's a good thing, and I'm going to go for moles of the silver chloride. We'll start with sodium chloride information. That's 125 milliliters. Then from milliliters to liters, so that I can use the concentration term to go from liters of sodium chloride to moles of sodium chloride. And then from moles of sodium chloride, we go to moles of the silver chloride. 1 milliliter, 10 to the negative third liters, and that's 0.150 moles of sodium chloride per liter of solution. And it's a 1-to-1 ratio of silver to sodium chloride. It's going to be silver chloride to sodium chloride. And hence 0.0188 moles of silver chloride can potentially be formed from the sodium chloride. We're going to do the same thing for the silver nitrate solution. So we're going to start by asking for moles of silver chloride, starting with that 150 milliliters of silver nitrate. And then, similar to what we did above, from milliliters of silver nitrate into liters of silver nitrate, so that we can use the concentration term to go from liters of silver nitrate to moles of silver nitrate. And then once in moles, we can go from moles of what we're given and into moles of what we're after. So out of moles of silver nitrate and into moles of silver chloride. 1 milliliter, 10 to the negative third liters. The concentration is 0.100 moles per liter. And again, it's a 1-to-1 reaction. Just because it's 1 doesn't mean you should get in the habit of not putting that in. And that would be a 0.0150 moles of silver chloride that we can potentially form from the silver nitrate solution. And how much can we actually make? The least amount. The smallest amount is the max we can form. We're limited by the reactant that forms the smallest amount. To complete the calculation, we're after the mass of silver chloride. We're then going to start step 2 with the just calculated moles of silver chloride. And now, using the molar mass, we're going to go from moles of silver chloride to grams of silver chloride. And using our periodic table, the sum of silver's molar mass, 107.9 grams per mole, and chlorine's molar mass, 35.45, or 143.4 grams per each mole. So that's 2.15 grams that can be formed. Again, does our answer seem reasonable? And I'm going to say yes. What's the concentration of oxalic acid solution if 50 milliliters are neutralized by 44.2 milliliters of a 0.751 molar sodium hydroxide solution? Okay, we have 2 preliminary steps here. What would they be? Coming up with the balanced chemical equation is 1. And when we balance this, acid with 2 protons, base with 1 hydroxide, I need 2 of each, so 1 oxalic acid gives me 2 protons, 2 sodium hydroxide gives me 2 hydroxides, 2 waters is formed in this, and 1 salt. What's that other preliminary step? Extending that bar. So we have moles over liters. And on to step 1, we're after the concentration. So moles of oxalic acid per liter of oxalic acid. Since we have this information given on sodium hydroxide, let's fully label these so we don't mistakenly use the wrong volume. or concentration, or number of moles. Okay, well, we're after 1 unit per another. We're starting with 1 unit per another, and so we have two single pieces of information, milliliters of oxalic acid and milliliters of sodium hydroxide. And let's be careful here, which is going to go on the top and gives us moles of oxalic acid. And if you're not really sure, then ask which is going to go on the bottom and take us to liters of oxalic acid. And I hope that tells us that the volume of the sodium hydroxide goes on the top and the volume of the oxalic acid goes on the bottom. Okay, on to step 3. Let's take care of our numerator. So out of milliliters of sodium hydroxide, can I go straight to moles of oxalic acid? No. How am I going to get to moles of oxalic acid? From moles of sodium hydroxide. And how do I get to moles of sodium hydroxide? From liters of sodium hydroxide. So first to liters, and then using the concentration term, we can go to moles. Now that we're in moles of sodium hydroxide, we can go straight to moles of oxalic acid. Do go back and scratch out those milliliters, scratch out the liters, scratch out the moles of sodium hydroxide, and circle the moles of oxalic acid. That just makes it jump out. We've taken care of our numerator, and we now still have to take care of our denominator. So out of milliliters of oxalic acid solution, can we go straight to liters? That's just a simple metric conversion. Let's scratch out the milliliters and circle liters, and what's left is moles circled and liters circled, telling us we've set this up correctly. If we've made a mistake, we would just have caught it, so make sure you do those steps. Scratching out will cancel, circling what's left. For the numbers, 1 milliliter, 10 to the negative third liters. For sodium hydroxide, that's a 0.0751 mole per liter solution. And the balance equation says 1 mole of oxalic acid to 2 moles of sodium hydroxide. Wasn't a 1-to-1 reaction this time. And 1 milliliter, 10 to the negative third liters. And that 10 to the negative third on the top and on the bottom cancel, so we don't have to put those on our calculators. And so simply 44.2 times 0.0751, divide 50, divide 2, or 0.0332 moles per liter. Does our answer make sense? And I'm going to say it sure seems within the right range of reasonability, so yes. I hope you're starting to get in the habit of asking when you're done with the calculation, or answering any question, does my answer make sense? That's the first step in critical thinking. Okay, on to new material, and we're going to learn about oxidation and reduction, where oxidation is the loss of electrons, so losing electrons is oxidation, and reduction is the opposite, the gaining of electrons. And I would point out that these two always occur together. For somebody to lose electrons, somebody has to gain electrons, and for somebody to gain electrons, somebody has to lose electrons. We need to be introduced to oxidation numbers, and this is either the ion that our element would be in if it's in an ionic state, or the type of covalent bond that's involved in, considering that the more electronegative element might have taken some of our electrons away. So essentially, it's the type of simple ion or the type of bond as if we had treated it like it was an ion. Okay, let me point out some things about oxidation numbers. And first is, if you have an element all by itself, it has an oxidation number of 0. So the nitrogen in the nitrogen molecule is 0. The sulfur in the sulfur molecule is 0. So anybody all by itself has an oxidation number of 0. If you exist as a monatomic ion, so a single element ion like the magnesium ion, then the charge on that ion would be your oxidation number. Those are both pretty straightforward. Then comes a molecular compound, or for this matter, covalently bonded atoms in a polyatomic ion. But anyway, if we have a molecular compound, we're going to know that the total number of oxidation numbers would be equal to 0. If we have an ion, like a polyatomic ion, then the total sum of our oxidation numbers would be equal to that charge on that polyatomic ion. And so if we have two elements in the compound, the more electronegative element is going to get the electrons that it wants, and then the less electronegative is going to give them up. Now, once in a while we don't have enough electrons, and we never take more than the outer shell's electrons. But the vast majority of the time, we have enough electrons. As I mentioned, the sum of all your oxidation numbers is equal to the charge of the species. So for a molecular compound with no charge, that will be equal to 0. If it's an ion compound, it's equal to the charge on that polyatomic ion. Now if we end up with 3 elements, then we're going to assign the most electronegative element the charge that it wants, and the least electronegative element the charge that it's going to have, meaning that it can give up. And then we would use the element in the middle to balance out. Normally the element that's taking electrons is oxygen, the one that's giving up electrons, meaning the least would be hydrogen, and then we might have somebody in the middle like carbon or chromium or sulfur or somebody else. Let's look at some examples. Okay, we're asked to give the oxidation number of all the elements in carbon dioxide. So we have a compound, a molecular compound with 2 elements in it, and so the sum of our oxidation numbers is equal to the charge on that compound, which of course is 0. So our carbon charge plus our 2 oxygen charges is equal to 0. Now we give the oxygen the charge that we expect it to take, and oxygen being our second most electronegative element is going to be quite strong in getting those 2 electrons. So our carbon charge plus our 2 negative 2's is equal to 0. Let me just distribute that to a negative 2. So my carbon minus 4 is equal to 0. Let's solve by adding 4 to both sides, telling us that the charge on the carbon, the oxidation number, it's not a formal charge, but it's the oxidation number of the carbon, we treat it like it would be a charge, is equal to positive 4. So our oxidation numbers were positive 4 for the carbon and negative 2 for the oxygen. And unless there's just not enough electrons around, that oxygen will always have the negative 2, and that's the main guy that's going to be taking our electrons. Okay, let's do another, this time for a polyatomic ion, and so the difference now is the sum of our oxidation numbers is equal to that charge on the polyatomic ion, that negative 2. So our 2 chromium charges plus our 7 oxygen charges is equal to negative 2. And then we assign the expected oxidation number, the negative 2, to the more electronegative element, the oxygen. So our 2 chromium oxidation numbers plus 7 negative 2's is equal to negative 2. Our 2 chromiums minus 14 is equal to negative 2. Let's add 14 to both sides. To get our 2 chromiums, have an oxidation number that adds to positive 12. Let's divide out the 2. So each chromium is in a plus 6 oxidation state. And you've noticed how I do my algebra. I put a bar, and then what operation am I doing to both sides of the equation? So you see we've added plus 14 to both sides in that previous step, and then the one after that we divided both sides by 2. Okay, now what is the oxidation number of each element in oxalic acid? Well, the sum of our oxidation numbers is equal to 0, same as the charge on the molecule. Now we give the expected oxidation number to the hydrogen, and it has 1 electron to give up, so it's going to be positive 1. And the expected oxidation number to the oxygen, and it wants 2 electrons, so negative 2. So positive 2 plus 2 carbons minus 8 is equal to 0. Let's just clean this up a little bit. Our 2 carbons minus 6 is equal to 0. Now we have to add 6 to both sides of the equation to get our 2 carbons equal positive 6. Lastly, we divide out the 2, so each carbon is equal to positive 3. You note in carbon dioxide was positive 4, and oxalate is positive 3, so don't expect it to be constant. And indeed, we'll find many nonmetals with quite a variety of different oxidation numbers. Okay, so again, the hydrogen was positive 1, the carbons were positive 3, and the oxygens negative 2. Okay, next on to redox equations, and these are the equations representing redox reactions. Now, when we go to balancing a redox equation, one thing that's going to be different than a regular equation is that we may not have all the elements present on both sides of the reaction arrow. That would be our first clue that we have a redox reaction that we have to balance. Now, many chemical equations that we've already learned to balance involve oxidation and reduction, but we were able to balance them with normal balancing means. But we'll see some examples where there may be oxygens on the left and not on the right, or hydrogens on the left but not on the right. Okay, now let me go through the steps in balancing a redox equation. And we have three big steps. The first step is to split the equation into two half reactions, one for the oxidation half and one for the reduction half. Then the majority of our work goes into step 2, where we balance each of our half reactions. Our final step will be to add the two half reactions together so that electrons cancel, but let me continue with balancing each half reaction. We have 4 sub-steps. The first is to balance the element being oxidized or reduced, and the vast majority of the time there's just one on the left and one on the right, but once in a while there may not be one and one. Then we balance the oxidation number by adding electrons. So for example, if we're going from a +5 to a +3, then we're going to gain 2 electrons. If we're going from +3 to +5, we're giving up 2 electrons. Our third step is, if we have an imbalance of charge, so we have some leftover negatives on the left or on the right, we're going to balance the charge by either adding hydrogen ions, positive ions, in an acidic solution, or hydroxide ions, negative ions, in a basic solution. If we're adding hydrogen, we would add it to the side that needs more positives. If we're adding hydroxide ions, we're adding it to the side that needs more negatives, so that when we're done with step 2C, it's charge balanced. The last step in balancing the half reactions would be to add water in order to balance the oxygens. And it automatically takes care of the hydrogens as well. I'm always amazed at how it just takes care of the hydrogens all by itself without any effort. Okay, at this point we would have the half reactions balanced, and so our third and final step is to add the two half reactions together so that the electrons cancel. So let's say, as an example, we had A going to A2 plus and 2 electrons, and then we had B3 plus 3 electrons going to B. Well, I have 2 electrons on the right, 3 electrons on the left. I need the same number on both sides. So whenever we're balancing something, we reach for the least common multiple, and of course that would be 6. So to get 6 electrons on the right, I'm going to multiply the first equation by 3, and to get 6 electrons on the left, I multiply the second equation by 2. And then when I add the two half reactions together, there should be no leftover electrons. If so, we made a mistake here. And you'll notice it's also charge balanced. It should already automatically be charge balanced. We normally shouldn't have to worry about it. So balancing a redox reaction, we have 3 big steps, with most of our work going into step 2, where we have 4 sub-steps. And we'll do one more example of an oxidation number, and then we'll get on to a redox reaction. What's the oxidation number of the chlorine and the chlorate ion? Well, we know that the sum of our oxidation numbers is equal to -1, and we know that that oxygen is going to be -2. And we also know that 3 -2s is equal to -6. Now let me stop right here. Let's go back to the original formula. We have the chlorine and 3 oxygens equals -1. So what I'm going to ask is, what -6 is equal to -1? Because I'm jumping all the way down to this third step. And I know the 3 oxygens gives us -6, so what plus -6 is -1, or what -6 is -1? So again, all the way back here, I'm going to be asking what -6 is -1, as I'm trying to find the oxidation number of the chlorine and the chlorate ion. So again, what -6 is -1, and we know the answer. 5 -6 is -1, and hence the chlorine is in a +5 oxidation state. But I'm going to be asking that, what -6 equals -1? Or if there's 4 oxygens, what -8 is -1? If there is 5, what -10 is equal to -1? Or -2, or whatever the charge on that polyatomic ion is. Okay, so we're going to use that right now when we have the chlorine and the chlorate ion plus iodide going to chlorine and chloride ion and iodine. we're asked to balance the following redox reaction, and the first thing we need to do is to identify which is being oxidized and which is being reduced. Well, what is the oxidation number of the chlorine and the chlorate ion? Well, what minus 6 is -1? Well, it's positive 5. We might write plus 5 above the chlorine symbol in the chlorate ion. Then the charge on the iodide and iodide is -1. Remember, the charged monatomic ion is your oxidation number. Same with the chlorine and the chloride, it's -1. And then what's the oxidation number of iodine in the iodine molecule? Well, of course, that would be 0. So the oxidation, well, who lost electrons? The iodine. It went from -1 to 0. And what was reduced? Well, that would be the chlorine, as it went from a plus 5 to a -1. Okay, so we split our reaction into half reactions, and now to balance each, we begin with the element being oxidized or reduced. And so for the iodine, the oxidation half reaction, I have 1 iodine on the left, 2 on the right, least common multiple is 2, so I need 2 iodines on both sides. For the reduction half reaction, 1 chlorine on the left, 1 on the right. As I said, the majority of the time there's just 1 on both sides. So really not a lot there to step 2A. Step 2B is to add electrons in order to balance the oxidation number. And I would point out, if you're gaining electrons, the electrons show up on the left. If you're losing electrons, electrons show up on the right. Now the iodide lost 2 electrons, going from I negative to 0 when there were 2 of them. And so 2 electrons show up on the right. Now what about the chlorine? Again, that went from plus 5 to -1. So the chlorine must have gained 6 electrons. So 6 electrons show up on the left. And at this point, we should have 1 with electrons on the left and 1 with electrons on the right. If not, somewhere you've made a mistake. Okay, step 2C is to now add hydrogen ions in an acid or hydroxide ions in a base in order to balance the charge. And I would point out that for the oxidation half reaction, we have 2 negatives on the left and 2 negatives on the right, so that's already charge balanced. But for the reduction half reaction, I count 7 negatives on the left and 1 negative on the right. If I'm adding positives, as I am in an acid, I'm going to add them to the left. I need to add 6 positives to the left to bring it to -1, to balance the -1 on the right. If I'm adding negatives, hydroxides are negatives, that's what we're adding in a base, I need 6 more negatives on the right, and so 6 hydroxides to the right. So step 2C, balance the charge by adding hydrogen ions in an acid, hydroxide ions in a base. We add hydrogen ions to the side that need more positives, and hydroxide ions to the side that needs more negatives. You rewrite this equation. And now step 2D is to add water in order to balance the oxygen. And there are no oxygens in the oxidation half reaction, so I don't need to worry about that. But in the reduction half reaction, well, I see in the acid 3 oxygens on the left and 0 on the right, so I need 3 more oxygens on the right, so 3 waters. Note how it took care of the hydrogens. In the base half reaction, we have 3 on the left, 6 on the right, so I need 3 more oxygens on the left, so 3 waters to the left. And again, note how it took care of the hydrogens. And at this point, we have concluded step 2, balancing each half reaction, which is where most of our work goes. We do have step 3 now, where we add the 2 half reactions together so that electrons cancel. It's going to be a little bit different between an acid and a base, since we had different half reactions in acid and base for our reduction half. And so here is our 2 half reactions in an acid. And now I see 2 electrons on the right, 6 on the left. The least common multiple is 6, so I need to multiply equation 1 by 3. Now when I add these 2 together, I get 6 iodides on the left, 1 chlorate, there should be a negative charge with that chlorate, 6 hydrogen ions, forming 3 iodide molecules, 1 chloride, and 3 waters. In a base, let's go ahead and balance this half reaction. Just let me bounce this reaction, so make this equation. So 2 electrons on the right, 6 on the left, least common multiple is 6, so we need 6 electrons on both sides. And then when I add them together, very similar, but do note I have hydroxides instead of hydrogen ions, and that of course changed my waters as well. Now in the event that I might have some spectators, meaning maybe I have waters on the left and on the right, I would subtract a smaller number from both sides, and we'll see an example of that in a little while. Okay, let's practice some of the things that we've just learned. We're asked to assign oxidation numbers to each atom in calcium perchlorate. Well, here's the formula of calcium perchlorate. The calcium is in its ionic state, so it's going to be +2. And now we need to find the oxidation number of the chlorine and the oxygens, knowing that the perchlorate ion has a charge of -1. So again, the perchlorate ion, ClO4, has a charge of -1. So the sum of the chlorines and the 4 oxygen charges is equal to -1. We give the expected oxidation number of oxygen. So chlorine plus 4 -2s is equal to -1. Let's distribute that. To get chlorine -8 is equal to -1. This is where I might be, just from the beginning, be asking what -8 is equal to -1. And of course that would be +7. So we saw chlorine in a -1 state, a 0 state, +5 state, and here in a +7 state. So we have to go through all the steps to determine that oxidation number. So again, the calcium is +2, the expected charge on the calcium ion. We just determined that the chlorine is +7, and the oxygens are the expected -2. Now we're asked for the oxidation numbers of each element in sulfuric acid. Sulfuric acid, H2SO4. Hope you recall how to come up with the formulas of acids. And I have now the sum of all these oxidation numbers is equal to 0. And then I would assign the more electronegative element its expected oxidation number, the least electronegative element its expected oxidation number, and I'll balance with the guy in the middle. So let me just go ahead and clean this up. +2 plus sulfur -8 is equal to 0. My sulfur -6 is equal to 0. What -6 is equal to 0? +6. So the sulfur is in a +6 oxidation state here. The hydrogen +1, to be expected, and the oxygen -2, which is to be expected. So again, when there's 3 elements, give the expected oxidation number of the least and the most electronegative oxidation. And now identify the oxidizing and reducing agents in the redox reaction below. Okay, the oxidizing agent, reducing agent. I haven't gone over this yet. Now let's think of a law enforcement agent. Does the law enforcement agent have law enforcement done on that individual? No, the law enforcement agent is the individual that does the law enforcing. And so the oxidizing agent is the species that does the oxidizing. In other words, if you're losing electrons, which means oxidation, this is the guy that causes you to lose electrons. So again, the agents are the ones that cause this function. So the oxidizing agents causes you to be oxidized, which means the guy who takes your electrons, and hence it itself is reduced. And the reducing agent is the species that causes you to gain electrons, and hence it itself is oxidized. So the reducing agent loses electrons, it's oxidized. The oxidation agent gains electrons, it's reduced. So I know this is kind of confusing. I didn't make up the terminology, but that's what this all means. Okay, so the oxidizing agent, which species is gaining the electrons? Which one's causing you to lose your electrons? Okay, let's start with copper. What's it doing? It's going from a 0 charge or a 0 oxidation number to a +2 charge or a +2 oxidation number. The copper is losing electrons, so it's giving up electrons, and hence it's the reducing agent. It itself is being oxidized. The hydrogens are +1 on the left and +1 in the water on the right, so hydrogen isn't doing anything different. And now what about the nitrogen? What's the oxidation number of nitrogen in the nitrate ion? Okay, well, we have 3 oxygens and a -1 charge, so what minus 6 is equal to -1? Meaning what times 3 times -2? So meaning what plus 3 times -2 is equal to -1? What minus 6 is -1, and that would be +5. So the nitrogen's in a +5 oxidation number in nitrate. What about in nitrogen monoxide? Well, the oxygen is -2, so the nitrogen must be +2. So the nitrogen went from +5 to +2 by gaining electrons. So the nitrogen stole the electrons, it's the oxidizing agent. The copper gave up electrons, it's the reducing agent. And now we're going to balance this reaction and identify which element's being oxidized and which is being reduced. We can balance this using normal means since all of our elements on the left are on the right. Okay, I see 1 sodium on the left, 1 sodium on the right. Least common multiple is 1, so there's 1 sodium on both sides. Then oxygen next. We'll let hydrogen be last. 1 on the left, 1 on the right. Least common multiple is 1. And now I have 2 oxygens on the left, and there's 1 in hydroxide, so I need 1 from the H2 molecule. Since it comes with 2, I need 1/2 of H2. And at this point, it's balanced. I'm going to go ahead and multiply the whole equation by 2 in order to clear that fraction. And we can always just rewrite these new numbers over the top of the old numbers. Again, here are the old numbers. Multiply the whole equation by 2. Here's the new numbers. Okay, and which species is undergoing reduction? So who's losing? Who's gaining electrons? And that's actually the hydrogen in water. It's in a +1 oxidation state. In the hydrogen molecule, it's in a 0 state. And which element is being oxidized? Well, the sodium is losing electrons, going from elemental sodium to the +1 sodium ion. Do note, oxygen's in a -2 state in water and a -2 state in hydroxide, so it didn't change at all. Okay, what is the oxidation half reaction for the reaction of zinc with hydrochloric acid? Well, oxidation means the element being oxidized, meaning it's having its electrons stolen, and that would be the zinc. The zinc's going from a 0 charge to a +2 charge. So there's our oxidation half reaction. And now we're going to balance the half reaction by first balancing the element being oxidized or reduced. And I see 1 zinc on the left, 1 zinc on the right. So that's already balanced with 1. Then, step 2b, we're balancing the oxidation number by adding electrons. And the zinc lost 2 electrons, so 2 electrons show up on the right. And now step 2c, we balance the charge by adding hydrogen ions or hydroxide, and do note we have a 0 charge on the left and a 0 charge on the right, which means we have to add neither, and that also means for step D, 2d, there's no oxygens to add, so no step 2d either. Now we don't have to write this all out, and in the short version we're not going to write it all out. So same question, and first the oxidation half reaction. Zinc goes to the zinc ion. Do know how to give myself a lot more room so that I can write in electrons, and hydrogen ions, and all the other things that might show up. Okay, and this might be different for an acid or a base, but 2 electrons show up on the left and on the right, and it doesn't matter what it say in an acid, and so we'll only show the acid. So let me just start over. Step 2a, balance the element being oxidized or reduced. 1 zinc on the left, 1 zinc on the right. Step 2b, adding electrons to balance the oxidation number. Going from 0 to 2, we lose 2 electrons, so 2 electrons show up on the right. Step 2c is to balance the charge, but it's already charge balanced, so we don't have to add hydrogen ions or hydroxide. And there's no step 2d since there's no oxygens. And now, what is the reduction half reaction for the equation below? Okay, the iron's going from +2 to +3, so it's losing electrons, so that's oxidation. What about the manganese? What's the oxidation number of manganese in the permanganate ion? Well, we know each oxygen is going to be -2, so what plus 4 times negative 2 is equal to negative 1? Or what minus 8 is negative 1? And positive 7 minus 8 is negative 1. So manganese is in a plus 7 oxidation state on the left. You might write that plus 7 over the manganese, because we're going to need that later. And then on the right, it's in a plus 2 state as ion, so it's plus 2 there. So the manganese in permanganate is undergoing reduction. Okay, to balance the half reaction, step 2A, we balance the element being oxidized or reduced. So one manganese on the left, one manganese on the right. Again, the majority of the time this is already balanced at 1 on both sides. Then step 2B, we're adding electrons to balance the oxidation number. And again, we went from plus 7 to plus 2. So 5 electrons are involved, and those 5 electrons show up on the left. You might think of this way. What plus positive 7 is positive 2? 5 negative 1s. So negative 5, 5 negative. So hopefully we can see that. The negatives show up on the left. Okay, step 2C, we're adding hydrogen ions in an acid or hydroxide ions in a base in order to balance the charge. And do note we have negative 6 on the left, positive 2 on the right. If I'm adding positives, I need to add 8 positives to the left to get positive 2 to balance the positive 2. If I'm adding negatives, then I need to add 8 negatives to the right to get negative 2 to balance, negative 6 to balance negative 6. And now step 2D, we add waters in order to balance the oxygens. In an acid, I have 4 oxygens on the left and 0 on the right. So I'm going to have 4 waters show up on the right. In the base, we have 4 oxygens on the left and 8 on the right, so I have 4 additional oxygens on the right, so I need 4 more on the left, so 4 waters show up on the left. Now my half reaction, my reduction half reaction is balanced for both an acid and a base. And you'll want to practice these 4 steps over and over until you get good at this. It's just like anything else, practice, practice, practice. Okay, same question, but do note if we do the short version, first we split into our 2 half reactions, and it'll be different for the acid and the base. And now step 2A, 1 manganese on the left, 1 on the right, so that's already done. Step 2B, we're balancing the oxidation number, and in both we're going from plus 7 to plus 2, so in both we're adding 5 electrons to the left. Now it gets different in step 2C, where we're adding hydrogen ions for an acid and hydroxide ions for a base. If we're adding hydrogen ions in an acid, how many hydrogen ions are we adding into what side? 8 to the left. And if we're adding hydroxide ions, which side are we adding it to, and how many? 8 to the right. And now step 2D, we're adding waters in order to balance the oxygen. I need 4 more oxygens on the right in the acid half reaction. So 4 waters show up on the right. And I need 4 more oxygens on the left in the base half reaction. So 4 waters to the left. And that's a coincidence that it happened to be the same number of waters. Don't expect it to always be the same number. Okay, now we're going to balance both half reactions for an acidic solution. Well, step 1, we split into our 2 half reactions, one for oxidation and one for reduction. So let's see who's undergoing oxidation and who's undergoing reduction. Well, what's the oxidation number of manganese in permanganate? Plus 7. What minus 8 is negative 1? Plus 7. What is the oxidation number of nitrogen in nitrite? Well, what minus 4 is negative 1, and that would be plus 3. So write that plus 7 over the manganese, the plus 3 over the nitrogen. Moving over to the right side, that plus 2 for the charge of the manganese is its oxidation number, so let's write plus 2 above the manganese. And now what about the nitrogen in nitrate? What minus 6 is negative 1? 5 minus 6 is negative 1. So the nitrogen lost electrons going from plus 3 to plus 5. The manganese gained 6 electrons going from plus 7 to plus 2. And now step 2A, balance the element being oxidized or reduced. One nitrogen on the left, one on the right. One manganese on the left and one on the right, so those two real step 2A. Step 2B, we're adding electrons to balance the oxidation number, and the nitrogen went from plus 3 to plus 5, meaning it lost 2 electrons, so 2 electrons show up on the right. And for manganese to go from plus 7 to plus 2, it gained 5 electrons, so 5 electrons show up on the left. That's step 2B. Step 2C is to now add hydrogen ions, since we're in an acidic solution, to balance the charge. So do note for the oxidation half reaction, I have 1 negative on the left and 3 on the right. Looks like I'm going to have to add 2 positives to the right, so I have negative 1 on the right, balancing the negative 1 on the left. For the reduction half reaction, I have 6 on the left, 6 negatives on the left, 2 positives on the right. If I'm adding positives, I need to add 8 positives to the left. And now step 2D, I'm adding waters to balance my oxygens. In the oxidation half reaction, I need 1 more oxygen on the left. In the reduction half reaction, I need 4 oxygens on the right. And again, do note the hydrogens just got taken care of by themselves. And now my third and final step is to add these 2 half reactions so that the electrons cancel. So I have 2 electrons on the right, 5 on the left, so that they cancel, it has to be the same number. So I need to balance them, and again, when you balance something, you're reaching for the least common multiple. And the least common multiple between 2 and 5 is 10. So I'm multiplying the first equation by 5, and the second equation by 2. So I have 5 nitrites, 5 waters, 2 permanganates, and 8 hydrogen ions on the left. Those 10 electrons have canceled. And then 5 nitrates, 10 hydrogen ions, 2 permanganates, and 8 waters on the right. Now you might notice that we have both waters and hydrogen ions on the left and on the right. So we're going to subtract the smaller number from both sides. The smaller number of waters is 5. The smaller number of hydrogen ions is 10. So that when I give my full net ionic equation, remember we always write the net equation, we don't have waters on the left, and only 6 hydrogen ions. And we don't have any hydrogen ions on the right, and only 3 waters. Sometimes you can complete both of those in one step, but if not, a separate step will do you well. To write a balance equation for the following in acidic solution, remember our steps. Step 1, we need to split it into 2 half reactions. We'll have 1 for oxidation and 1 for reduction. And so let's look at the chromium and see what's the oxidation number of chromium in the chromate ion. Well, what plus 4 negative 2s is negative 2, or what minus 8 is negative 2, and that would be positive 6. So let's write plus 6 above the chromium and chromate. On to the sulfur. What is the oxidation number of sulfur in sulfite? Well, what minus 6 is negative 2, and that would be positive 4. We see that the chromium in the chromium 3 ion is plus 3, so chromium went from plus 6 to plus 3, so there's our reduction half reaction. What about the oxidation number of sulfur in sulfate? Well, what minus 8 is negative 2? Positive 6. So the sulfur in sulfite is being oxidized to the sulfur in sulfate, where the chromium in chromate is being reduced to the chromium in the chromium 3 ion. Okay, now it's time for step 2A, where we are balancing the element being oxidized or reduced. And I see one sulfur on the left, one on the right, so that's balanced. One chromium on the left, one on the right, so that's balanced. On to step 2B, balancing the oxidation number by adding electrons. Well, the sulfur goes from +4 to +6 by losing 2 electrons. So 2 electrons show up on the right. The chromium goes from +6 to +3 by gaining 3 electrons. So 3 electrons shows up on the left. On to step 2C, where we add hydrogen ions. This is acidic solution. So we add hydrogen ions to balance the charge. So I see for the oxidation half reaction, 2 negatives on the left and 4 on the right. So I'm going to add 2 positives to the right. And that makes it -2 to balance the left. In the reduction half reaction, I have 5 negatives on the left, 3 positives on the right. So it looks like I need to add 8 positives to the left to bring it up to +3 to balance the right. And now step 2D, we add waters in order to balance the oxygens. In the oxidation half reaction, I need 1 more water on the left. In the reduction half reaction, I need 4 waters on the right. And now time for step 3, where we add these 2 half reactions together, so that what happens? So that electrons cancel. So I see 2 electrons on the right, 3 on the left. The least common multiple is 6, so I need 6 on both sides. So I multiply equation 1 by 3 and equation 2 by 2. And then I have 3 sulfites, 3 waters, 2 chromates, and 16 hydrogens on the left, 3 sulfates, 6 hydrogen ions, 2 chromium 3 ions, and 8 waters on the right. And I had waters and hydrogens on both sides, so I reduced them by the smaller number. So I subtracted 3 waters from the left and the right, so no more waters on the left, and we're now down to 5 waters on the right. We had 6 hydrogens on the right and 16 on the left, so we subtracted 6 from both sides, giving us no hydrogens on the right, and reduced ours on the left down to 10. So very much like we did in the previous problem, only I did 2 steps in one. If you feel like you need to do 2 separate steps, by all means, please do so. And that concludes today's lecture on oxidation, chapter 4.4. We learned about oxidation and reduction, the loss and gain of electrons. Redox reactions are essentially where we have oxidation and reduction occurring, and many reactions are oxidation and reduction reactions. Most combination reactions, most decomposition reactions, and to some degree combustion reactions and replacement reactions. But for specific redox reactions or redox equations, we might see that maybe oxygen doesn't show up on the left or on the right, or hydrogen doesn't show up on the left or on the right, meaning we'll see an element that doesn't show up on both sides. That's our biggest clue that we're using this redox procedure. And then normally you're also told to essentially balance this by 2 half reactions or some clue of that type. Okay, and that concludes this lecture.